In this video, we're going to introduce the capacitor, which is another passive element. In earlier videos, we have talked about resistance and what role it plays in the circuit, Ohm's law and all that. And we talked about inductors with its relationship between voltage and current, which is L di dt. Voltage is equal to L di dt. And now we're going to introduce another element, which is called a capacitor. And a capacitor is simply two conductors. So let's get a pen. So it's two conductors that are separated by dielectrics. In other words, the upper and lower one are conducting. Electricity moves through them. And the middle part separates them, so it's a typically non-conducting material. Sometimes you could use air. You could have two pieces of metal, for example, separated by air. That's a capacitance. Or you could have in the middle some sort of a plastic polymer that separates them. So that's basically the construction of capacitors. Of course, there are many different kinds that can be implemented. Some capacitors actually have liquid inside them, but fundamentally that's what they are. They are two conductive material that's separated by a separate one, and then the capacitance, which is measured in farad, it's F-A-R-A-D, farads. It's basically calculated based on its construction with this equation, which is going to be A is the overlapping area of the conductors, D is the distance between the two conductors, and E is the permeability of the material we are using as a dielectric. Okay, so that's basically what that C is all about. Now, in the circuit, of course we don't want to draw the physical diagram, and instead we kind of draw capacitors typically like this. Now most capacitors, the non-electric capacitors, are they don't care which side is positive, which side is negative, but there are some that may be drawn with the positive side and the negative side. But let's for our discussion here, we're going to assume we have more of a standard ceramic or polymer-based capacitor. And in those cases, it's a passive device. So if the current is flowing in this direction, I of t is flowing in this direction, the voltage that would be created is going to be plus minus, much like resistor, much like inductor. And then that would be the voltage across it. Now, if you will recall earlier, we had discussed all the passive elements together and their relationship to voltage and current and all of that. In this particular case, the relationship that ties in a capacitor, the relationship that ties the I and V together is basically I of t equals to C dV dt. So voltage still is measured in volts, I is measured in amp, and C, of course, is the unit is farad. So farads is what we use to measure capacitance. Great. Now, if you look at this equation, again, this equation to capacitor is every bit as important as Ohm's law was to the resistance. So if this is the case, you notice that if we draw, let's say, a voltage V of t, and if the voltage is changing, the slope of the voltage times C really drives the level that the current will have. So as long as the slope is constant, you're going to get a constant current coming in. Now, if voltage stops changing, if voltage stops changing, then you will find that at that point the current will go to zero. So as this equation is showing, is that the rate of change of voltage is what drives the current. Great. Now we can also write voltage in terms of current, if you integrate both sides and clean it up, we're going to get 1 over C integral of from time t0 time t of I of tau d tau. In this particular case, we also have to remember that there is a initial condition. So the capacitor could have charge stored in it from at the time t0. So when you write this equation and integrate, you have to consider what the initial condition for it was as well. Okay, great. So now we are this far, and then the only other thing we need to talk about is power and energy. As we talked about before, power P of t, you measured in watts. It's equal to a derivative of energy or work. Sometimes it's written E of t or WT, doesn't matter. So this is energy or work. Sometimes it's also WT. And so power is a derivative of that. Of course, energy and all that is measured in joules. So I can write this E of t as integral of power with respect to time, right? So that's another way of figuring out the energy or the work. And this, from the earlier work, we know power is always equal to V times V of t times I of t dt. From the earlier equation, if this is the energy we are talking about in a capacitor, then the current in a capacitor can be written as C dV dt, which means at any point in time, if I want to find out what the energy is at that particular point in time, all I have to do is do 1/2 C V of t squared. So that's a quick way of finding work or energy, and of course this is a C. Okay, and the unit for those, of course, would be watts second or joules. So the one thing to take away is that the capacitor is a passive device, therefore the current comes in and you're going to generate a voltage, and this is the key relationship that relates voltage to current for capacitor. Everything else, as you saw, can be easily derived from this basic characteristic equation of capacitors.